Hello friends, welcome to my new data structures and algorithms in Java tutorial series video. Friends, in this tutorial we will discuss how to represent a binary search tree in Java. In our previous tutorial we actually discussed about the binary tree. We saw that each and every node in the binary tree had two children, one was the left child and one was the right child. So a binary search tree is a special type of binary tree in which the data is organized in an ordered manner, which helps us in faster search and insertion of the data. So how binary search tree helps us in faster search and insertion of data, we'll see later. First we will discuss the three properties which makes it a binary search tree. So here in the diagram you can see a binary search tree which satisfies these three properties. So the property 1 says the left subtree of a node contains only nodes with values lesser than the node's value. So what does it mean? Let's suppose if we take a node having data as 6. So all the nodes to its left like 4, 2, 5, they have values lesser than 6. So if you see, there are 3 nodes to the left of 6. And if you compare the values of these 3 nodes with 6, you will find that 4 is less than 6, 2 is less than 6 and 5 is less than 6. So all the nodes to left of a particular node should have values lesser than the node's value. And similarly, if we go to right of any particular node, then all the values should be greater than the node's value. So if we take the example of node having value as 6 and if we go to its right, we see there are 3 nodes having data as 8, 7 and 9. All the values are greater than the node's value. So here in the binary search tree, we are keeping the data in ordered form, that from a particular node, if we go to its left, we will only find the values lesser than the node's value. And if we go to its right, we will only find the nodes having values greater than the particular node. So friends, the third property says the left and the right subtree each must also be a binary search tree. So friends, here we saw that node 6 is following these two properties, that all the values to its left are lesser than the node's value and all the values to its right are greater than the node's value. And in a binary search tree, these two properties should be true for each and every node of the binary search tree. So for example, if we take a node having value as 4, then we can see that to its left there is only one node and its value is 2, which is less than 4. And if we go to its right, then there is only one node whose value is 5, which is greater than 4. So 4 also satisfies these two properties. And similarly, if you are on node 2, then it doesn't have any left and right child. Therefore, it also satisfies these two properties. And if these two properties are satisfied by all the nodes of a tree, then that tree is called as binary search tree. So here in this diagram you can see that it is a binary search tree. So suppose if I change a value here and I make it a value as 8. So here you can see that node with the value as 4, if we go to its left, we are getting a value lesser than the node's value, and if we are going to its right, then we are getting a value greater than node's value. So 4 satisfies these two property. But if you go to the parent of 4, here you can see the value is 6 and we know that all the nodes of a left subtree should be lesser than the node's value. So here you can see 4, 2, 8 should all be less than the node's value, but 8 is greater than 6. Therefore this is not a binary search tree because these two properties should be true for each and every node. And if you are on a particular node, then we take all the nodes of its left subtree and right subtree and we compare it with the node's value. So here you can see 4 and 2 are lesser than 6, but 8 is not lesser than 6. Therefore it is not a binary search tree. And similarly, if I take a value of 5 here, then you can see that if we are at node 8, then if we go to its left, we see that value of 5 is lesser than 8, and if we go to its right, then we have node 9 and value of 9 is greater than 8. So 8 satisfies these two properties. But if we go to the parent of 8, which is nothing but 6, so here you can see that it is not a binary search tree, because from property 2, the right subtree of a node contains only the nodes with values greater than the node's value. So if we see the right subtree from the node 6, we see it has 3 nodes, and all these 3 nodes should have values greater than 6. But here you can see 8 and 9 have values greater than 6, but 5 is lesser than 6. Therefore, this tree is not a binary search tree. So friends, all these 3 properties, if satisfied by each and every node of a binary tree, then it becomes a binary search tree. Below these 3 properties makes the search and insertion of data faster, because let's suppose if we want to search for a value 5 in this binary search tree, then we simply check the value 5 with the root of the tree. So here you can see that 5 is not equal to 6, and as it is a binary search tree, we know that 5 must be lying somewhere to the left of this tree, because it satisfies the 3 properties, and we know that the left subtree of a node contains only values lesser than the node's value. So we know that 5 must be lying somewhere to the left of node 6. So from node 6 we traverse left and we reach to 4. And also here you can see when we are traversing to node 4, we are simply discarding all the nodes of the right subtree, because we also know that 5 can never lie to the right of 6. So let's suppose if we had a binary search tree having many nodes, then we could have simply discarded half of the nodes and we would have continued our search to either right or to left of the search tree. So friends, if we compare 5 to 4, then we know that 5 is greater than 4. So 5 must be lying somewhere to the right to 4, and then we simply traverse to its right and we discard the left subtree of the node 4, and finally we found the node having data as 5. So friends, when we want to insert a data into binary search tree, we usually follow these 3 properties only. So let's say if you want to insert a node having data as 10, then we simply start from the root node. We check the value of root to the data which we want to insert. So here if we compare the value 6 with 10, then we know that 10 is greater than 6, therefore it should be inserted to its right. So we traverse to its right and we see there is one more node. So we compare this value with the value which we want to insert. So here 10 is greater than 8, therefore we know that 10 must be inserted to its right. So we simply traverse to its right and we find there is one more node having data as 9. So we check that whether 10 is greater than 9 or not. So here 10 is greater than 9. So we go to its right and we find that there is no node, because 9's right is pointing to null. So we simply insert node at that place. So friend, this is how search and insertion of data gets faster in binary search tree, because in each iteration we discard half of the tree, as we know that we either want to traverse to right or to left. So friend, this is the usefulness of binary search tree. Moving ahead. So friend, if we see the structure of tree node in a binary search tree, then it is very similar to binary tree. That this tree node is nothing but the inner class of binary search tree, which has basically the 3 properties. One is the data property, to hold the data, and other 2 properties are nothing but the references to the left subtree and the right subtree. We also provide a constructor to this tree node class which takes in a data part. So whenever we want to create a new tree node, we simply pass in the data property, and left and right property actually points to null. So friends, let's go to Eclipse and see the implementation of binary search tree.